Hello everybody, I'm Ajay Singh. Welcome to my talk on neutralization based reclamation algorithm. This is the work done under the supervision of Professor Trevor Brown and Professor Ali Masizadeh at Multicode Lab in University of Waterloo. So before we begin, a quick outline of our talk today. First we will talk about safe memory reclamation problem and then some of its desirable properties followed by existing solutions to it. Then we'll discuss our own contribution, which is a neutralization-based reclamation algorithm, followed by results and conclusion. So people who have programmed concurrent data structures would know that freeing memory in these data structures is not a straightforward task. Let's see why. So consider a simple linked list and a thread T1 which is trying to find node N3 on this list, and another thread T2 which is concurrently trying to delete node N2. So let's say T1 while moving towards node N3 stops at node N2 and sleeps or context switches while holding the pointer to node N2. Simultaneously, the thread T2 moves towards the node N2, unlinks it and frees the record N2. Later, if thread T1 wakes up and tries to access this freed node N2, it will crash. So this is typical case of use after free in concurrent data structures. And if we observe closely, this happens because while thread T2 was trying to free the node N2, another thread T1 held a private pointer to the same node. Safe memory reclamation is this problem of deciding when is it safe to free a record in concurrent data structure so that use after free error could be prevented. Intuitively speaking, a record or a node is safe to free when it is unlinked from the data structure and no thread holds a pointer to it. Typically, a record in a concurrent data structure goes through multiple states. Initially, it is in unallocated state. Then, if it gets allocated, it enters into uninitialized state. Later on, a thread might insert a record in the data structure where it enters into the reachable state. And at that point, it becomes reachable from the entry point of the data structure. And after some time, a thread might remove the record and it enters into the retired state. Typically, in a SMR algorithm, a record, whenever it is retired, is actually stored in a thread local private buffer. So after this point on, it's the responsibility of safe memory reclamation algorithm to decide when it is safe to free the record. And at that point, it enters into the safe state. And after that, it could safely be freed to the underlying operating system and the record enters into the unallocated state again. So these SMR algorithms are expected to have certain properties. First of them is the performance. So each SMR algorithm should have high performance. In other words, it should have minimal overhead on the underlying data structure. Also, these algorithms should bound the garbage they produce. That means the number of unreclaimed records in the thread's private buffer should be bounded at all the times so that programs using it do not exhaust the system memory. Also, these SMR algorithms should be usable, which means that they should require minimal programming effort, they should not depend on any compiler construct, or they should not rely on any complex hardware primitive which might not be easily available on the commodity hardwares. Last but not the least, these SMR algorithms should be applicable. That means they should apply to as many data structures as possible. Existing safe memory reclamation algorithms can be categorized into three broad categories. First, reference counting based algorithms. Second, epoch based algorithms. And third, hazard pointer based algorithms. It turns out that reference counting based algorithms have low performance and conditionally bound the garbage. Meaning, if garbage has cyclic pointers, then the number of unreclaimed records could grow unboundedly. Reference counting based algorithms are slow, which also raises an important question that if we are ultimately going to use a slow reclamation algorithm with our data structure, then why should we bother about using or optimizing the data structure in first place? On the other hand, epoch-based algorithms have really high performance, but the problem with them is that they have unbounded garbage. So any data structure or software which uses them could actually exhaust system's memory. And loosely speaking, it is nicer to have a bound on the garbage of a data structure which uses these reclamation algorithms. Last, hazard pointer based algorithms are interesting in the sense though they perform low in most cases, but they have bounded garbage. But the twist in the story is that they do not apply to many data structures which might have where threads might traverse over the logically deleted nodes. I mean to say a sequence of logically deleted nodes. So in fact, we surveyed 18 recently proposed data structures, and we found out of them to 15 data structures hazard pointers do not apply. So here's a selective list of data structures. As you can see, this is a quite diverse list of data structures. For more detailed table and discussion, we refer audience to read our paper. So inspired by these problems in the existing algorithms, we proposed a neutralization based reclamation algorithm which has high performance, bouncy garbage, is highly usable, and applies to many data structures. Typically, these data structures have a pattern where long searches are followed by short updates. This means the operation has a read phase and a write phase. So whenever a thread is trying to reclaim a record, a thread could either be in a read phase or the write phase holding the pointer to same record. So how do we resolve use after free error in this case? Well, if a thread happens to be in the read phase, since it hasn't done any updates or modifications yet in the underlying data structure, it could simply restart if the reclaimer somehow communicates to it its intent. On the other hand, if the thread happens to be in write phase, can we do the same? The answer is no, because the thread might be in middle of updates, and if we restart it, it might leave the data structure in an inconsistent state. So instead, what can be done is, if somehow this thread knows the number of records it would access in the write phase, it can simply reserve them before entering into the write phase. So this phase actually is can be thought of as a conceptual reservation phase, where it reserves its record it will require to carry out its updates in the write phase, and it can be sure that any concurrent reclaimer cannot reclaim it because it has already reserved it. So NBR actually leverages this data structure design pattern to realize a safe memory reclamation. Let's see at a high level how NBR leverages this observation to realize safe memory reclamation. So in NBR, whenever a thread retires a record, it actually stores that in its own local buffer. And after it has reclaimed enough, it has retired enough number of retired records, it will send neutralizing signals to all the other threads to express its intention to reclaim. So these signals are nothing but POSIX signals. Let's say a thread T3 has acquired enough number of retired records, and then it sends neutralizing signals to all the other threads in the system. And if a thread receiving this neutralizing signal happens to be in the read phase, let's say thread T1 is in read phase when it receives this signal, it can simply restart because it hasn't done any changes to the underlying data structure yet. In doing so, it actually promises the reclaimer that it will discard any pointers which it might hold in T3's retired buffer. So this is actually a reader reclaimer handshake where T3 neutralizes thread T1 in the read phase, and this thread T1 actually guarantees back to T3 that it has given up all the pointers in its buffer so that T3 can go on and reclaim its records. On the other hand, if a thread receiving the signal happens to be in the write phase, it would have already reserved its pointer. So in a way, writer actually guarantees the reclaimer thread T3 that it will save all its pointer before entering the write phase. And the reclaimer T3 in return guarantees that it will not reclaim those records. So reader reclaimer handshake and writer reclaimer handshake together ensure that safe memory reclamation is realized in NBR. So any thread, after it has sent signals to all the threads in the system, can be sure that no thread will hold any unreserved pointer in its buffer. Therefore, it can simply go on and reclaim or free all its retired records, leaving any reserved records behind. Let's see with help of an example how easy it is to apply NBR to a data structure operation. We'll use lazy list as an example. So in this particular operation, the read phase begins with read of head node and ends when pred and current nodes are identified. So one can simply invoke begin read phase function here. Additionally, one needs to call or invoke neutralization checkpoint, which is basically a call to 6 set jump that implements the restart behavior for the threads in the read phase. And the update phase in this particular function begins with the locking of pred node and ends with the unlock of current node. Additionally, we also know that pred and current nodes are the only two nodes which would be required to carry out this update operation. So one can simply invoke and read function, which internally reserves the pred and current nodes and also marks the beginning of the write phase. For more complex data structures which have multiple read and write phases, you can read our paper where we discuss in detail about the applicability of NBR. So let's see how NBR performs. Well, it turns out for small machine with low number of threads, NBR scales really well, but for large number of threads, it doesn't scale that good. So in this plot, which is generated on a 144 thread machine with 4 sockets, NBR actually scales well up to 72 threads, but after that, its performance plateaus. So this overhead actually comes from many signals which are sent while a thread reclaims its buffer of retired records. And this overhead actually increases with increasing number of threads. As can be seen in this plot, the overhead is actually manageable up to 72 threads, but after that, the overhead starts dominating, leading to the flat line in case of NBR. So this motivated us to propose an optimization over this plain NBR, which tries to reduce the number of signals sent in the system. We named this algorithm NBR Plus. And as it can be seen, it performs up to 2 times faster than the plain NBR algorithm, and it maintains its trend even under oversubscription. NBR Plus actually uses observation that a thread can piggyback on another thread to reclaim its own record without sending signals of its own. Let's see how it is done. Assume our thread T1 retires a record R at this point, and later another thread T2 actually neutralizes all the threads in the system. So let's say it starts sending signal at time t and finishes sending signal at time t prime. So after this time t prime, it is guaranteed that no thread will hold any unreserved pointer to the record R, which is in thread T1's buffer. So that essentially means T1 can actually free this record R if it is not reserved after time t prime. In other words, T1 can piggyback on T2 sending signals to reclaim its own records. So in NBR Plus, whenever a thread's buffer is partially full, instead of sending signals of its own, it actually starts monitoring for a thread which might be sending signals. And if it successfully monitors a thread which starts sending signals and finishes sending signal after it has actually started observing for such a thread, then a thread can reclaim its own buffer as well. So in summary, it really doesn't matter which thread is sending signals. As long as a thread can reason about such an interval where a thread has started sending signals and finished sending signals, then a thread can reclaim its own records as well. Let's move on to experiments now. So we evaluated NBR on a 4-socket machine with 192 hardware threads. In this talk, we'll talk about 2 data structures mainly. First is binary search tree due to David and others, and second is Brown's AB tree. For additional experiments on lazy list and Harris-Michael list, we refer you to our paper. So we compared NBR with Jabra, which as far as we know is the fastest EBR variant. And we also compared NBR against hazard pointers, interval-based reclamation algorithm, quiescent state-based reclamation algorithm, and RCU. So this first plot here is for external binary search tree due to David and others. It's for 100% updates and a tree of size 2 million. So y-axis shows here millions of operations per second, which is throughput. and x-axis is for shows number of threads. So as you can see here, NBR Plus actually significantly outperforms algorithms like hazard pointer, IBR, RCU, and QSBR across all the threads. And the dotted line here shows the data structure with no reclamation, just for our reference. So most interesting comparison here is with Debra. So as you can see here, Debra actually performs slightly better than NBR up to 96 threads, but after that it actually flattens out. And on the other hand, NBR Plus actually scales up really well and performs much better than Debra after 96 threads. So and that happens even under oversubscription. So you may wonder what is the reason of the crossover point which happens around 96 threads. So it turns out that Debra is susceptible to delayed threads. So these delayed threads actually cause accumulation of large number of retired records in each thread's buffer of retired records. So these large buffers, when eventually they get to free themselves, it actually bottlenecks the underlying allocator. So so this actually overhead due to this bottlenecking of allocator actually worsens with increasing number of threads. So that explains performance of Debra after 96 threads. Now, for more realistic workloads, let's say for 50% updates, again we can see here NBR Plus performs much better than algorithms like hazard pointer, IBR, QSBR, and RCU across all the threads. But the interesting point here is the crossover point with Debra. So you may notice that in comparison to 100% updates, the crossover point now occurs much later, that is at 126 threads. So this is because the overhead due to bottlenecking actually becomes less severe in case of less number of updates. Because if the number of updates are less, the each thread's buffer actually gets filled up slowly, and that actually leads to less frequent bottlenecking of underlying allocator. And again, as in the previous plot, the Debra actually after 144 threads scales poorly. In fact, it degrades, but NBR Plus actually scales up and performs better under oversubscription. Now moving towards more read-intensive workload, that is for 10% of updates. Here we see that, again, the trend continues. NBR Plus is much better than QSBR, hazard pointers, RCU, and IBR, and matches Debra. So Debra is actually slightly better for threads below 192, but after that, NBR Plus actually takes over and performs much better than Debra. Moving on to Brown's A/B tree. So here again we see that the trends are similar as we saw in external binary search tree. Thing to be noticed here is that Debra actually performs much better than NBR Plus up to 72 threads, and then it sort of scales down. But NBR Plus again continues its upward trend and scales up gracefully. You may notice here that we haven't compared NBR with hazard pointer for Brown's A/B tree, and the reason here is that Brown's A/B tree cannot be used with hazard pointers. So it only made more sense to compare NBR only with NBR Plus only with Debra, because as far as we know, Debra is the high performing EBR based variant so far. And again, for more realistic workload, which is like 50% updates, here Debra again performs better than NBR Plus up to 144 threads, and after that NBR Plus takes over, and up to 252 threads it maintains its supremacy over Debra. Now for 10% updates, both of them are closer, but Debra actually performs slightly better up to 192 threads, and after that again the trend is that NBR Plus scales better and Debra actually scales down. So NBR Plus turns out to be performing good after 192 threads for 10% updates only. So in conclusion, We propose a neutralization based reclamation algorithm which is fast, bounds garbage, is usable, and applies to many data structures. A point to be noted here is that there are some data structures to which Nbr Plus may not apply, but hazard pointer does. For example, Harris-Michael list. For a detailed discussion on applicability of Nbr Plus to data structures and other things which we have not covered in this presentation, please read our paper. Thank you.